Yeah, so I just saw that. Creating an XML parser, I watched a bit of that. The query verse, that's, yeah, I saw a bit of that. Code, Google Code in and beyond. I believe that's the girl from Hong Kong that was pretty cool. Yeah, using VS Code, I saw that. Dancing with friends and enemy. What is that about?
My name is Jesse Bencourt. Today I'll be talking about voids, the dance, friends, and enemies. Voids were first defined by Craig Reynolds in his 1987 paper, Flocks, Herds, Schools, a Distributed Behavioral Model. In this paper, Reynolds defines a flock of voids as a collection of objects which exhibit polarized, non-colliding, and aggregate.
I'm so glad I watched this presentation.
This gives the impression of intentional, centralized control for the flock. But this is actually emergent complexity from the interaction between individual voids. So, to simulate these complex flocking behavior, we only need to simulate the individual behavior of the individual voids, such that they avoid collision, match the velocity, and stay close to their nearby flockmates. This produces a recognizable representation of natural behavior, and it is similarly delightful to watch. However, the voids I am visualizing are not that original paper, but rather a 2013 post on the Wolfram Community Forum by Simon Woods, where he uses expensive math software for frivolous entertainment by describing the simple void interaction rules as a series of dance steps. The dance with friends and enemies are as follows. 1,000 dancers assume random positions on the dance floor. Each randomly chooses one friend and one enemy. And at each step, every dancer moves a little bit closer to the center of the floor, takes a large step towards their friend, and a small step
cool and
away
all,
from
but
them. Also, at random intervals, one dancer will re-choose their friend and their enemy. Here you can see the original dance in very terse Mathematica. Just want to show this because the most very nice to visualize, I create a void type, aim of the dance. The default dance is one for every friend. All parameters of the dance.
That's cool.
So here you step size. Rapid plot elements that Mackie provide.
So it's a talk about Mackie.
Do block.
Okay.
Let's interact with the dance now. Here we can see a dancing flock with default parameters.
Oh, that's pretty cool. Is there a slide on why Mackie was chosen?
Mackie reframes are
nope.
K dancers choose.
It's pretty cool. Yeah, I think I saw that formula. It's also pretty.
So there's three parts to this. The first part is a special term to represent the syntax. So you have a random effects term structure that holds the left-hand side and right-hand side. Right? You define a method for apply schema, right? That takes in a function term with the type of the special syntax you want to overload and returns a different type of specialized term, right? So here, in this case, a random effects term in the specialized context, right? So this will only happen if you're trying to fit a mixed model. And then finally, you need a method for actually creating the numeric representation, the specialized numeric representation of it. So in mixed models, this is a specialized structure called an REMAP that takes advantage of some of the special structure of the regression problem to create an efficient sort of sparse representation. Now, mixed models goes way beyond this actually and overloads a bunch of other things too. So it overloads this slash to represent kind of nesting, so you can nest groups within other groups. It also defines special functions like zero core and full dummy, which are important for controlling the variance covariance structure in these in the groups. Okay. So I think this is actually really, when we hit on this solution, it wasn't obvious at first, but I think it actually is quite elegant because it relies on the normal Julia mechanisms for adjudicating disputes between packages about who owns a particular function, a particular method, a function, and type signatures, right? So you could define a very wide context type where your syntax applies, but then it can be easily overruled if somebody comes along and defines a narrower type that applies only to their specific model, right? And of course, you can always steal syntax, right? So there's nothing stopping you in your package from defining a method for a function term for a base function, and a model type that some other package creates. Right? But again, that's type piracy, right? That's a thing that we are aware of in the Julia community. We sort of know how to work around that, right? So this takes this sort of thorny problem of creating custom DSLs and lowers it down to a place where the sort of normal Julia mental model of multiple dispatch and working together across packages can work. Right? Okay, so I want to talk just in the last couple minutes about some mistakes we made, and I think that are still sort of outstanding problems. So one is that there's this conflicting pressure to move stuff out of the macro to make it more useful at runtime. But the problem is you end up defining a lot of methods, overloading a lot of base functions, stuff like that, then it can end up taxing the compiler unless you're really careful. This is still a problem. This is, I think, the biggest problem with the current implementation. Another mistake is that three-way dispatch is hard. You end up with a lot of method ambiguity. It's not always clear where to specialize things, just from a design perspective. I think the biggest outstanding design issue is that the context only comes in at the very last stage of that pipeline before you're actually generating the array. It comes in at the apply schema stage. And what this means is that there's no context-aware way of generating the schema based on the data. And this is a problem because you might, in a mixed model, have a grouping variable that has like 100,000 or 1 million levels. We can fit models like that now, right? But what the schema is trying to do is construct a contrast matrix, which is a sort of a k by k-1 dense matrix. So if you do that with a grouping variable that has 100,000 or 1 million levels, you're going to get it out of memory error, right? And there's no way to, without manual intervention, tell the schema function that you don't need to construct that whole matrix, right? But you still want to know what the unique levels of that variable are. Also, things like if you want to fit like a spline basis, that needs more information than the default extractor extracts, or could be expected to extract, right? You want to know something like, where are good places to put the knots in my splines, which is basically the quantiles of the data. And expecting the quantiles of the data is like, you need to know how many quantiles you're trying to extract, things like that. So it's not something that you can do without knowing the kind of context that you're going to be using the model in. Okay. The last thing is like, what the hell happened to performance? Performance on this system is frankly not as good as it should be, and a big part of that is that we're hitting the compiler really, really hard, because if you look.
That's actually quite interesting. Got asked by someone on the internet, on Twitter, about what is actually worse about Julia. I think I should just give an honest answer. Okay. Alright, that's done. Right.
Look at the type of the structure that's returned by this formula. There are type parameters here for every single one of the subparts of this, right? So this is a formula term that has a term on the left side, a term on the right, a tuple of terms on the right side, a constant term, a term, a term, a term. You'll see a whole bunch of interacting numbers that actually just intentionally let it run off the screen because it's like one of these horrible type signatures. Okay, so in the future we're trying to get rid of as many of the type parameters we can, not abuse the compiler so much. We're looking into better representations of non-special calls to the function term. We want to make row-wise table support first class, right? So the biggest thing for this, two biggest things here are like online or parallel schema extraction and an in-place model calls methods. And finally, we want to have some mechanism for allow context-aware schema creation. This is more of a design issue. We don't really quite know how to resolve it at this point. Okay. And finally, we need to sort of settle on the actual modeling API. I haven't talked about like the models part of the stats model. Just sort of like the formula part. So the modeling API is still sort of from the data frames age, and it's not great. That needs a lot of work. Yeah. Okay. So that's all. Thanks for coming, and hope you learned something. And if you have questions, I'm eager to hear them, and please reach out.
AppCube function, which takes in.
Okay, so it's got some specialized function. Oh, that's pretty cool.
In the AppCube function now.
I guess it's not general enough. So
again, we have to include the function we defined.
Hello everyone, welcome to my JSurf talk. So what is JSurf? I would describe it as a connection between Julia and JavaScript with a reactive DOM and a server with some routing. It can be used for dashboards, wrapping JavaScript libraries, and writing web pages.
That's interesting.
It has a similar scope to React.js in some ways, but it has quite a different approach and is of course not as mature and big and usable. How does it work? Let's create a simple web page with it. The core is that you have a DOM handler that is called whenever you get a request. So if you request this web page here on localhost, this function will get called. And with this JSurf DOM module, you have all the different HTML tags wrapped that you can use. And then this uses actually Hyperscript and is a pretty nice Julia abstraction over HTML. Then you can run this handler with this application constructor here on a port and URL, and then you get this here. One of the core abstractions in JSurf is using observables everywhere. So, for example,
it's often frustrating when you want your package to depend on amazing package A, but doing so introduces ambiguities in base that Hey has not eliminated. Okay. The way to avoid this often is to simply put in is empty, test, detect ambiguities. Okay. I didn't know about this. That's interesting. I really should put this in my package. Learn something new. So let me put it in right now in case I forget. So test folder, test ambiguities. Of course, I need to rename that as .jl. Ah man, my keyboard's not great. Okay, and of course I need to test this for JLBoost. And try that. Using JLBoost, using test. Let's give that a spin actually. I think the JLBoost. Whoa. I have some requirements that are not resolved. Okay. Seems to be some issues with JLBoost. What's my JLBoost project? This looks fine. Oh, I'm confused now. Anyway, test JLBoost. Yep, I am just taking a break from watching the Julia thing, just testing these things. I saw some nice posts. Oops. Hello? Oh, some so laggy. Using a package is so laggy. Oh, test failed. 1. Why is it failing? There's an error during testing. It doesn't really tell me. It doesn't tell me why I failed. It's complaining about HTTP. Oh wow, this test is too strong. I don't want to turn this on. Okay, that's fine. That's an interesting thing to learn about there. Alright, what else is there? CSV segment fault in project environment. CSV. So activate my project. Read this. Straight segment faults. Interesting. Oh, FreeMin7, thanks for following. What's going on here? I added CSV to my project. Seven is a T. 7 is a T. Cool. I don't even know what that means. This guy's running into seg faults. in your username. 7 is a T. Free mint. I see what you mean. So I should say your name is Free Mint. Let's see if I can remember that next time. Okay. I'm reading some Julia forum. See if I can help this guy. Okay, very good. I got it. Very interesting. Yeah. Well, something interesting about my username. You like the VS Code talk? Yeah, open source. Yeah, I remember that. There's actually 2 VS Code talk. I watched that already. Yeah.
And so on.
Yeah, I think I watched it already.
So this is a really rich. I'm just going to list some out, but SSH adoption that works by.
Yeah, I watched the VS Code talk and I also watched the Juno talk. That's why I try to completely uninstall Juno because it's like there's no point anymore. Well, I really can't help this guy, so I'm just going to reply with the most generic thing. I have a cake. Today is the anniversary. I joined the Julia Discourse community. That's interesting. Oh. Okay, let me just I want to tweet about this. I often get paranoid when I have a long word. Just check the spelling double sure. That's interesting. I'll post that. Alright. Do you like Juno features which aren't inside? Yes. You're sad about Juno and code merging. Do you like Juno features which aren't inside VS Code yet? Yeah. The biggest one, to be honest with you, I couldn't have written the Parquet writer without the Juno inline evaluator feature, because the Parquet metadata is very complicated. It's multi-levels, but in Juno I can just click through each level and see exactly what is stored where, and that was not possible with VS Code or with REPL. So that was actually really great. Oh, Juno does VS Code crash on you? I think the biggest problem I had with Juno was that it always gives me the feeling that it's hanged. It's like I couldn't do anything. Like, oh, what's happened? I don't know. It just hanged. And after a while, it just got really annoying. So I switched to VS Code. Yeah, the inline evaluation isn't nearly as good. I don't know how to let me just try this thing, right? Let me try this. Because I obviously made the Parquet writer and improved the Parquet reader, but I just haven't had time to update it. So if I'm here and say, I'll see how good the thing has become. So if I'm doing this using Parquet I'll actually check my Parquet. Let's just activate the Parquet test environment. Def Parquet. I think in Parquet there's a function called metadata. Okay, so yeah, so using using Parquet, and for the life of me I can't remember where any of my Parquet files are, so let's try that. Parquet, try that. That looks okay. So that's my Parquet. Oh, what the hell? That's my Parquet file. That's the location of my Parquet file. Put a raw around it. I think if I just do Parquet.metadata, then I'll see how good this is. You see the metadata it's humongous. Like you can't make sense of it. So unless you have the inline thing, let's see how good the inline. No, it's inline. No, it's nowhere near as good, man. I can't. There's no way I can inspect what's inside it. Oh man, nah, it's not even close. Yeah, so that's one thing I'll definitely miss. It's just not gonna work. On the other hand, this object viewer might work. Yeah, that's better. That's what I'm more used to. Okay, then I don't actually need Atom anymore, because look, I can get everything I need. I can look at this complicated metadata and figure out exactly where everything is. I think so. Yeah. So look, it's like many layers. If I don't have the ability to click through, I wouldn't be able to understand anything in the Parquet metadata. It's just nuts. Like, there's no way I can look through this, but I can look through this. Yeah. 1.5. I thought I saw a news that 1.5 was released today. Is it not true? I heard some good things about. Maybe it's not true. Oh no, it's not true. It's not being released yet. It's only still RC2. I guess RC2 is only for a couple of days, so I don't think a few days it's not really ready. Yeah, thanks open sources. Yeah, on Julia, on the tab on the right, on the left works for me. Yeah, Atom definitely much slower. I don't know, I don't care about the RAM as long as it's responsive, but it's not responsive. I guess that's my biggest problem with it. Yeah, nah, I don't think 1.5 is out yet. But yay! Okay, this is a quick question on floats. Let me check this out. Wondering if someone could explain what's going on. Okay. I don't even know about this. Oh, okay, the info macro just prints something. Yes, I remember that. So what is the issue? Extra digit in the, why isn't the first float value this? The subtraction gives 0. Oh, so the question is, when you do the info on 32, why does it print less? Oh, why does it print this? Okay. Well, yeah, I think this guy explains it. Yeah, it's not that big a deal. Someone's answered it already. Same constructions, less code. Yeah, actually, convert and promote rule also confuses me. Man, I'm not sure if this sentence even makes sense to me. So, nope, so I'm not going to read this further. It's too hard. Bug in linear algebra plus plots combo. Also, the indexing of always eats all my battery. Oh. You mean Adam does the indexing? Never got it to finish? Or VS Code does the indexing? Yeah, indexing is so bad. I was trying to use PyCharm, but every time it opens up, it indexes a bunch of crazy things. So I just gave up on PyCharm. I don't use that anymore. I just go straight to VS Code. It's just so annoying. I don't think the fact that you have an i9 has anything to do with this, but I could be wrong. Rank A. Rank of A is 5. Rank of B is 0. Rank of B is 5. Oh. Wow, that's a weird bug. That's the weirdest shit stuff I've seen. This is just weird. It does look very weird. I have no answer for that. It's interesting. Could it be that some of this function is manipulating a global B without telling it? Well, anyway, I don't think I can resolve this. It's too weird. Yeah, VS Code does a lot of indexing. Yeah, actually, I haven't noticed that, honestly. Seems to be fine for me. VS Code. Yeah. Well, I'm really glad that I can have a good object browser now, I think. I'm not sure, I can't remember if this was here before. So I can look through all my stuff now, which is pretty cool. Yeah. Oh wow, VS open sources. That's kind of weird. I don't know why that might be the case. Okay, abstract or abstract array. Yeah, I'm not sure. Theoretically, if the compiler is quite strong, then it should, these two different codes should make no difference at all, because it should compile that away. Because, but I don't know, maybe I'm not understanding this compiler thing properly. Yeah, I mean that's what I would expect. I don't know why there would be a difference, but anyway, can't understand that. Alternative to pipelining table operations like filter, how to speed this up? Kai. I used to have a co-worker called Kai, but I highly doubt this guy is the same co-worker I had, because I don't think the co-worker that I knew would be interested in Julia as a programming language. I found the following chunk. Moving on, yes. Okay, this is a major bottleneck in the code. For each ID, uses pipelines to filter out the data for that ID, creates a column object and builds the myops time. Okay. Data. Okay, so he's got a table of a column table. He filters it. Okay. And converts it to a column again and creates this reproducible example. Oh, that's very long. I'd be interested. It is got resolved, but kind of hard to see what's going on. Well, could he just be talking about compilation? Scene construction. Pointer to as a parameter. Okay, what's going on here? You want to pass a pointer? Well, maybe. Yeah. Understand that Julia, you don't have to do that. It's fine. Can't support Windows. Cool, that's done.
Could create this observable here that creates a color, and one of the main functionalities in observables is that you can map over them and create new state from this. So color CSS, if you map color, every time color updates you want to return this new string. So how does this look? It looks like this. You can set a new value here, green for example, and then if you look at this here, you see that it's this new string. And you can register callbacks with this, so they will get called whenever this value changes. Now this is the main abstraction here, and we can use it everywhere in our DOM. So if I reload this with the new observable, we see that it's green, and then we can set it back to red pretty easily. One can also update observables from the JavaScript side. So we have this little string macro here to encapsulate JavaScript code, and we even get nice syntax highlighting from the Atom IDE. And how the updating works is that we can splice in any Julia observable in this expression here, and then we can call the JavaScript function update observable and set it to a new value. So if I run this here, I will have this button here and can change the color by clicking this button. There are a few other ways to execute JavaScript. So we already saw that we can pass it as HTML attributes, but we can also run a JavaScript function whenever a DOM element loads in our DOM. So here we call alert when the button gets loaded, and we can call a JavaScript function whenever an observable updates. So let's run this here and reload. We first get the hi from JavaScript, which gets executed on load. And then whenever we update the observable, we get another alert. So if we click this, we get another alert. So these are the main ways to run JavaScript on your page. And yes, these are the basic building blocks to create interactive HTML JavaScript applications. Now, you can also include existing JavaScript libraries or CSS styles. So for example, here I have a couple of CSS library, the MUI library, for example. I've written a little slider style example, asset, and some image, and you can all include them as assets. And run this here. And now we will get this new styled app. And as you can see here, on any slider move, we show the slider value, and we can see that this corresponds to this.
Interesting.
The little weirdness here is, as you can see, these are unsigned
got a bunch of
8 values. That's because we're using method pack, which packs any value to the smallest integer or float it fits into, which is very effective but can be a bit annoying. As you can see, we already also have a link here. It doesn't do anything yet, but we can make it work by adding a new route to our app. For this, let's just rename this to DOM handler 1 and use that here as a new route. And you can add it as simple as this, with the pattern for the route here, and then the handler one call.
Alright, see you open sources.
DOM function, which sets the context, and the
can do some hackering.
But no, this should work. See, here we have this.
Yeah.
That we had before.
Message me.
No,
alright, see you next time.
They're new and pretty cool. So here we just use our slider. I'm using actually Tailwind here to very quickly style our little example via Tailwind classes, which is a lot easier. And then instead of just returning the DOM, we return this record state map, which will record all states triggered by the slider. And that combined with JServe export standalone will enable you to export a standalone static app. Let's see if it works here. This is still live on our server. Just squares this value on the Julia side with the Julia process. And now we can export this as a standalone, which will just put all the used resources and assets and the state map into one folder with an index.html, which can be served, for example, by live server, or put on GitHub.io, or put into your documentation. Let's see if it works. So here, this is our static app. There's no Julia process running, and that's just static HTML, and it works very nicely. In my market talk, you can see very complex examples using this for serving complex interactive plots. Thank you, and I hope you enjoy using JServe and learning about it.
Hi, everyone. Welcome to the talk. The agenda for today is to describe how we use Julia to build a new kind of cloud-native relational database management system that supports knowledge graph use cases. I will explain some of this as we go. I hope the content in this talk will be interesting to anyone who knows Julia, but it will make the most sense if you know something about databases, cloud computing, compilers, and knowledge graphs. So briefly, what is a knowledge graph? According to Wikipedia, a knowledge graph is a knowledge base that uses graph-structured data model to integrate knowledge and data at scale. Okay, it's a way of representing knowledge and data that humans and machines can understand. And I believe that future systems will be built with knowledge graphs as a foundation, where each component or service in that system will either be learned via machine learning, or it will be declared and executed via a sophisticated reasoning engine. You know, think SQL or Excel spreadsheets on steroids. And only as a last resort will we have to instruct the computer step by step how to perform a certain task. So how do you build a knowledge graph management system? Well, first you have to answer two questions. The first question is, how do we represent graphs? And the second question is, how do we represent knowledge? So how should we represent graphs? Our answer is with relations. And if you've worked with graphs before, you know there are different ways of representing them. But a very common way is to represent the edges in a graph with an edge relation that maps source node to destination node if the graph is directed, or just connects two nodes if the graph is undirected. And so here's a quick example of that. Of course, relations are a universal abstraction. You saw just now how we represent a graph with a binary relation. We can also represent a hypergraph where you have edges between 3 or more nodes as an n-array relation. Functions are also represented via graphs, tensors, sets, bags, and so on. And the cool thing about the relational paradigm is that you can separate the abstraction from the implementation. Relations can be mapped to adjacency lists, to B trees, to hash maps, to a variety of data structures that might be more or less suited for a particular data set and particular payload. Second question is, how should we represent knowledge? And our answer to the second question is that you should represent knowledge with a relational language. And we built a small and simple core relational language that supports one core type of structure, which is the relation. And relations can then be used to, can be specialized to represent other things like functions and tensors and graphs and so on. There are 3 language constructs in this core language. Identifiers, so how you name things, name variables and name relations, introduced via bindings. The second is abstraction, so anonymous relations, or the equivalent of a lambda in functional programming. And the third is application, which is like function application in a functional language. And there are 7 types of formula operators. The first 6 you know very well: conjunction, disjunction, implication, negation, the fixed point operator, which is recursion, and first order quantifiers, which you can use to build aggregations and reduce things, reduce relations, you know, sum across the rows of a relation. And the third type of operator is less well known, but it's a second order quantifiers, and lets us make statements like there exists a relation that satisfies the following properties, and is a really nice way to integrate solvers and optimizers into the language, because that's what you would use a solver, for example, to find a relation that satisfies a set of properties. And from this core language, we built on it to get tables in SQL for the business analyst community, likes to work with tables in SQL, tensors and linear algebra for the data science and ML community, graphs and navigational queries for the graph community, and then JSON and graphical, which are sort of preferred abstractions by the developer community. And we implement these abstractions as views on common internal representation. And the key insight here is that the table, the tensor, the graph, the JSON abstractions are just views on graph normal form relational schema, or as it's sometimes called, a 6 normal form schema. A graph normal form relation is a key plus at most one other column, so it's irreducible. You can't break it down into components that you can reassemble with the relational language. It just basically, it can't go any smaller. And most people have never heard of graph normal form and 6 normal form because they're not practical to implement in traditional SQL relational databases, because you end up with way too many relations, way too many tables, and then you end up with having to join them all back together, which is super expensive in the context of those types of database engines. So you might ask, can we have the abstractions and high performance? And I'm here to tell you that yes, we can, as long as we use a new generation of joint algorithms, optimizers, and data structures to make that work. Okay, the rest of the talk is going to be about that. So our system is built with 3 design principles in mind. One is leverage. Let's just leverage work that other people have done, in particular cloud computing. Let's leverage all the infrastructure, in particular the object storage systems that come with cloud computers, that in a sort of traditional database, the storage manager would take 70% of the code, whereas here we're going to basically leverage AWS or Microsoft Azure or Google's investment in their respective object store systems. Okay. The other thing, of course, we're leveraging is modern languages and compilers, specifically Julia and LLVM. We're also building a system that is clever and strong. Most systems today, when they're built with performance and scalability in mind, they basically achieve that performance and scalability by throwing hardware at the problem. We want to go faster and be more scalable by avoiding work, not just doing the same units of work with many, many more workers. And we also pay attention to the constant factors, and we manage, we do latency hiding, manage latency hiding the right way in sort of the 7-layer deep memory hierarchies that exist today in terms of global storage, local storage, RAM, global RAM, socket RAM, NUMA node RAM, L3 cache, L2 cache, L1 cache, the registers. Anyways, managing that memory hierarchy is very important to us, and making sure that the constant factors are good, along with having strong support for automatic parallelization and specialization. And then finally, we aggressively simplify and consolidate the system. And in fact, there are 5 core capabilities that we can compose elegantly in ways that cover a broad range of use cases. And the system today already does a lot, and it's less than 100,000 lines of code. It's hard to imagine that the core of the system is going to grow beyond 200,000 lines even after we add the pieces the few pieces that are missing. Okay, so let's talk about these 5 capabilities one at a time. The first is a query compiler that basically eliminates the interpretation overhead that you see in many database systems. Most database systems implement query evaluation via an interpreter. In our system, we wanted to compile the query down to machine code and run it as if it was, written to be compiled. Okay, so a very brief example here. You see the select query. The select in our system, the select query will be optimized using a very sophisticated semantic query optimizer, and the resulting execution graph is then emitted as a Julia program, which we give to Julia, and Julia analyzes that, optimizes that further, and emits LLVM IR, and then LLVM takes that and emits machine code that runs very efficiently. And this back, this is machine code that executes that SQL query there. Okay, we benchmark this against best-in-class systems for doing business intelligence analytics, and as you can see here, we do quite well on this TPCH benchmark on a scale factor of 100. 100 gigabytes of data. We do quite well relative to the best-in-class systems, and we do very, very well against popular systems like Spark, where, as you can see here, the closed source optimized version of Spark running on 16 cores takes more than 4 times the time that we run the same 22 queries on 1 core. Okay, so 16 cores run 4 times slower than we do, because systems like Spark don't pay attention to constant factors and interpretation overhead and so on. You can learn more about how we do this by taking a look at Jamie Brendan's JuliaCon 2018 talk, or Nathan Daly's JuliaCon 2019 talk. They explain in more detail how we do some of this query compilation and so on. All right, the next major building block is incremental maintenance. As the cliche goes, the only constant is change. And the goal of incremental maintenance is to minimize the cost of change. And ideally, if the thing that you're computing before the change doesn't change that much after the change, then you want the system not to do that much work. So in general, small changes don't lead to, small changes in input don't most of the time lead to big changes in output. And if that is the case, we want to do a little bit of work to incrementally update the computation that we've already done. And that's really important for implementing things like integrity constraints, live programming, online learning, and a lot of other important components of a relational database and a knowledge graph management system. Okay, we treat incremental maintenance as just another compiler optimization. To illustrate this, consider the simplest of relational programs, a single hop exploration and knowledge graph. Our compiler will rewrite it into a derivative with respect to changes in nodes and edges. Okay, so these are sort of the derivatives. And the compiler introduces counts for each tuple to capture changes, like is this piece of information supported more or less by the changes that are being made. And the counts and the derivatives efficiently maintain the query result as the knowledge graph changes. And we support incremental maintenance on any program you can write in our relational language, including those that involve aggregations, negation, and existential quantification, recursion, and so on. It's really important to support full language. Most database systems, if they support incremental maintenance, they support it on a fragment of the language. So like any other optimization, incremental maintenance comes with trade-offs because we need to remember previous results to use them in incremental maintenance. So effectively, we're trading off space and time. Ideally, we don't want the user to have to worry about these trade-offs, and users shouldn't need to know anything about incremental maintenance other than it just works. And Julia helps us with this because it makes it easier to gradually optimize the program as we learn more about how it's being used. So we start off by assuming that all inputs are static, unchanging, and optimize the program for sort of single use. But as transactions come in and start to update the inputs, we recompile the affected program fragments to their derivatives, and then start keeping track of the counts in order to do efficient incremental maintenance. Okay.
Wait, something funny has happened on Twitter. I hate this job advertisement so much and can tell this job would absolutely suck. It's in Melbourne, South Yarra. Wanted data Yoda. Data analyst scientist magician. 45 to 65,000 a year. For context, 45 to 65 is what a graduate, like just fresh out of uni, would get in their first year, roughly, you know. Yeah. So this is getting interesting. Okay. I'm just gonna have a read of this. Yuck! My screen is crawling. It's fun job ads, frustrating formal. There's nothing more terrifying. It's aggressively informal. Ping pong table from the fact they're paying you. They aren't paying your superannuation. Oh my god. That's not good. always pay people superannuation. Oh man. See, on LinkedIn you can't do LOL, but it's pretty funny. Okay. Data analyst Ryoda. Switched on, okay. Any old data scientist? Okay. No, okay. I don't think he means to be, is that a word? What's a word for holding prejudiced views about elderly people? Ageist or something, I don't know. It hasn't been a thing. He's looking for data Yoda. Maybe I shouldn't. That's actually pretty funny. Huh? Has already been shared? What? Where's this guy based? I can't share this on LinkedIn. This is so weird. That's a hard question. Z is false, so that's in a global environment. Sets out a function called foo. This is in language R. This is y equals z, but inside this function z gets replaced as true, and y is returned. Okay. So foo, what's going to return? Foo y equals z, what's going to return? So let's work this out. So when y was called here, when you call this function, that's already called. And at this point, y is attached to false. So then you change it. This z is different to this z, so y is put in the right one. Okay, so so this one should put in false. Actually, I'm not sure. I'm guessing. Y equals z, so that's false. False is false. So it should return false, false. But there's no false, false. So my whole reasoning is completely wrong. So it should be true, false. Should be false, false, right? Tomorrow, okay. Well, I thought it'd be false, false, but yeah, I don't think I understand. So z in this case, so yeah, in this case y is equal to false, that's for sure. It comes into here. I guess this time what? I thought it'd be false, false, but it could be true, true. If it's not a trick question, oh, false, false is here, so it should be false, false. Well, let's see if I get it correct tomorrow. What was that? 3 notation.
We also support incremental compilation, also known as incremental view adaptation or incremental metadata maintenance. I'm not going to talk about that today. Please check out Nathan's talk at this JuliaCon on JL about how we do that and the vast ramifications of that. This also work is based on work done by the Rust community, and the incremental maintenance work that I described earlier is based on work by Frank McSherry, who's built systems called the differential data flow. The next capability is immutable data structures. So let's talk about a key part of our performance story here, which is the data structures. In a busy database, you have multiple database versions being manipulated by many threads. And the question is, how can we design fast data structures for this? One possibility is shared immutable data structures, but these suffer from synchronization overhead, either in the form of mutexes or bus locks, or so-called lock-free data structures. Another possibility is purely functional data structures, which don't require synchronization, but have significant copying costs, typically logarithmic in n. We're using a hybrid approach here that gets us the best of both worlds, which we call MUTs, which is short for mutable until shared. In the MUTs discipline, data structures local to the thread are mutable and can be destructively updated, which avoids much of the overhead from copying data every time you need to update it. Data structures shared between threads are always immutable, which means that no locks are required and there's no cache coherence overhead. The root pointer uniquely identifies the state of the data structure is. So the MUTs discipline achieves isolation, the I and the ACID properties are sometimes here about being important for databases, which while also scaling to many cores. Okay? So we've been developing a library for efficient MUTs data structures, and I'll talk about two of these data structures briefly. The first is MUTSDict, MUTs Dictionary, which is our version of JuliaCon dictionary, and soon to be available as a community contribution. So we're going to put it out there for anyone to use who's interested in this kind of data structure. In addition to the usual dict interface, the MUTs dictionary provides branch and mark mutable methods. The branch method returns a mutable copy of the dictionary in constant time. A thread can call a branch, make a sequence of modifications to the dictionary by calling setIndex, then call mark immutable before sharing it with other threads. And making an efficient MUTs dictionary took some careful data structure design. This table compares the asymptotics of Julia's dictionary to MUTs dictionary. Will provide constant time lookups using getIndex. SetIndex runs slightly slower for the MUTs dictionary, n to the 1/7, but this is much faster than mod time for small, medium-sized dictionaries that fit in memory. And the cost of SetIndex gets cheaper the more changes you make to the version. An interesting footnote here is that the worst case performance of SetIndex for Julia's dictionary is linear time when a hash table.
That's interesting. This is the first time I've heard about the MUTs discipline. So mutable until shared. I learned something new in this one.
Besides this trigger. But the worst case SetIndex for a MUTs dictionary is only n to the 1/7, which makes it much better suited for applications where updating is managed. Now we get to the intended use cases, which is having multiple versions of the same dictionary coexisting at the same time and branching new versions. With Julia's dictionary, if you want to make a copy of the dictionary that won't reflect changes made by the threads, you need to do a deep copy, which takes linear time. With the MUTs dictionary, the branch operation takes constant time. We also provide an efficient set diff to quickly iterate the differences between two versions of the dictionary. This runs sometimes proportional to the number of changes in two versions, plus a little bit more. So the MUTs dictionary is our go-to data structure for in-memory dictionaries. For durable storage and big data, we also have to have page data structures. In this case, in our case, we've implemented a D-epsilon tree in Julia using the JLBoost.jl package, a package that we also built and open source. If you're not familiar with page data structures, a D tree is optimized for disk storage, where each node in the tree is, for example, 64 kilobytes, it can be more, it can be less. And the branching factors are enormous. For example, a node might have 1,000 children. In a traditional D tree, a setIndex or an update operation would navigate to the tree to find the appropriate leaf node and update or insert the record there. This incurs massive overhead if you want to do copy and write versioning, because you might have to clone a 64 kilobyte page just to insert a 16-byte record or 8-byte record. Instead, we use a write-optimized variant of a D tree called the D-epsilon tree. In the D-epsilon tree, we make the tree a bit deeper, for example, twice as deep, and devote the space to squeeze up in internal nodes for buffering changes. So setIndex will just write to a change buffer in the root page. And when that root page buffer gets full, the buffer changes gradually spill down to the tree to the leaf pages in a way that minimizes dirty pages. Okay, so you're batching up your updates. This is a perfect fit for the MUTs discipline because it reduces the cost of versioning. It also good fit for cloud storage because scattered updates are concentrated in a few pages that are cheaply sent to cloud storage on AWS S3 or Azure Cloud Storage. Implementing page data structures in Julia is quite painless. We use again blob.jl package for page layouts. This lets us read a binary page from a local storage subsystem and interpret the page image as a blob contained in a Julia struct. Inside the struct, we find fields like tree height, number of records, vectors containing chain buffers, and child page pointers. Blobs.jl defines custom get field and set field methods. So when we write node.height, that gets compiled into a dereference of the pointer to the height field in the page image. And when we need fast performance for queries, we can get raw pointers to vector data in the page and emit code that's very competitive with C and C++. Okay, if you want to learn a little bit more about this, check out Dr. talk at JuliaCon 2018. We talked about low-level systems programming and high-level Julia. Last thing I'm going to talk about here, in terms of sort of immutable data structures, is the pager. The pager helps us do automatic memory hierarchy management, where we don't have to worry if the data set that we're operating on is larger than the memory count. We basically organize the data into pages and pages as they are needed. Unfortunately, historically, pagers have been implemented at a high cost in terms of the query performance, and that high cost exists even if the data fits in memory. And that's sort of led to the creation of in-memory databases that don't have pagers and just basically load all the memory, all the data into memory. Okay, some recent work by Thomas Lyman and his students has led to the development of new pagers that basically give us the best of both worlds. We get the out-of-core memory management, but we don't have to sacrifice in-memory performance when the data fits in memory. Okay, the pages role in a database is to manage the storage layers and transitions of data or pages between them. Like I just said, accessing data that is in memory is fast, but many machines have limited memory, so the pager also takes care of picking pages from memory to make space for new ones. A good pager not only loads and fixed pages, but minimizes and balances latency twists. Traditionally, that might mean handling transitions between local storage and memory gracefully. For a cloud-native database such as the one we're building at RelationAI, it means overcoming the much larger latency gap between local storage, ESB, for example, on Amazon, and network round trips for cloud storage like S3. Implementing this capability was very straightforward in Julia. Julia lets us implement pager design cleanly without any needless boilerplate. For example, the structure to the right holds all central data structures to implement the pager design taken on the left. We manage the memory for the pages when we create, when we want to, and rely on Julia's garbage collection and other protections for the rest. This makes it easier to use and debug tricky code simply because of the list. Making the pager thread safe and straightforward thanks to lock defaults provided. By using single lock, we can guard our in-memory structures and then convert our single-threaded pager to support task parallelism with only 2 additional words. For example, to commit multiple pages in parallel, we simply had to add spawn macro. Easy peasy. And dropping down to a low-level interaction doesn't mean sacrificing simplicity. As discussed earlier, using JLBoost.jl to manage access to raw pointers and to generate compact data layouts for our pages. In the code example to the left, we're allocating a new page pointer and add div to the page table, and it looks just like any other Julia type because it is. We also benefit from Julia's tooling for tuning debugging, especially in this critical component. We all know Julia's interactive REPL environment, and we're benefiting from its code exploration macros, which we use to spot type instability and define scary bugs like register corruption caused by latent LLVM bugs, which we all know exists. Our colleague Nathan Bailey also wrote a JL library, and we use it to interactively dive into the generated code. pprof.jl and memory.jl also helps profile analyze page and optimize things further. Okay, the next component here that I'm not going to talk about is optimal join algorithms. I'm going to skip that, but sort of this is an algorithmic innovation that we came up with. You can look at just these optimal join algorithms. And then the final, the fifth component is semantic query optimization or optimizer that takes a relational programming's input and then produces an execution graph that optimizes the time and space that it takes to evaluate the relational program. Unfortunately, I don't have time to talk about that either, but it helps us just do amazing things, including optimize machine learning. Here's a quick example where we converted a sort of learning problem that traditionally requires that you build a data frame and send it to TensorFlow from taking something like 12,500 seconds to taking 18 seconds. And so the impact is enormous by emphasizing the brains part, which I'm not going to cover here today. So in closing, we think the relational paradigm is very important because it lets us separate the what from the how. And in so doing, we can automate a lot of tricky bits on behalf of people who use relational systems. I'll let you read the slide. And it's really a step towards the holy grail of automatic programming as described by Jim Gray in his Turing Award and is referenced here by Professor Don Torrey at the University of Texas, and talking about how the relational query optimization system is an example of or a major advance towards automatic programming. Okay, and in conclusion, we built the world's first intelligent database, a knowledge graph management system that uses knowledge and data captured in enterprise databases to learn and reason. Please reach out if you have any interest in working with us or using the system that we built. We'd love to hear from you. Thank you very much.
Hello, and welcome to my talk about nonlinear optimization algorithms in Julia for GPUs. This is a follow-up talk to last year's talk, Modeling in Julia at Exascale for Power Grids. This talk last year went around our ECP project and how we plan to scale up to exascale using Julia. Now, there have been a lot of changes which mainly revolve around GPU, which I will go into in a few moments. And these meant a lot of changes in our project. This work is done by Adrian, who has a long experience in power systems and has also contributed to the solver PETSI. And myself, I have a background in automatic differentiation. Our group at Argonne revolves mostly around optimization. The upcoming supercomputers will mostly rely on GPUs, and that's a surprise since that was not planned that way. It was only planned that half of the systems would support GPUs and the other one would be more multi-core. So that means if we want to make use of these machines efficiently, we have to make use of the GPUs, and this also had consequences for our project. Our project revolves around power systems, which are modeled as a flow problem in a graph. You have sinks, you have sources. The sources are the generators. The sinks is the demand and the consumption. And we simulate one such power flow. And we want to have the optimal power flow, so the most cost-efficient one, so that you use your generation in the most cost-efficient way. And we parallelize over the number of contingencies, which means our network on a normal operation has to account for the fact that a generator might go down, and the system has still to be operational if one generator or line goes down. Now, with renewable energies, we have less inertia in the network, which increases uncertainty and also calls for more accurate models. Power system models are a complex network class of problems. Other examples is traffic, internet, pipelines. And the main feature is that the connection is irregular, and the problems tend to be to have a high condition number in the underlying solvers. So what we actually solve per power flow per case is the optimal power flow, so the most cost-efficient way of generating power. So the power generation goes into the cost function and has some parameters associated with each generator. Then we have the Kirchhoff laws of a flow problem, so what flows in must flow out, and we have the line limits. And these line limits tend to be a hard part of the problem. They are inequalities, whereas the Kirchhoff laws are equalities. The optimal power flow has a long history of solving, and from the 50s or 60s, it started out by being simulated as a linearization. So you solve actually DC power flow and find the optimum of that. That's actually still what is being used nowadays in the industry. Now we use AC power flow that makes the functions non-linear, and interior point is currently the state of the art. So what you do is the inequalities move into the cost function and become these barrier functions, which make the underlying linear system that you solve at each Newton iteration even a worse condition. The de facto standard solver for solving this problem is IP-opt. It's also used in JUMP for NLPs. The condition of the underlying linear system can be really high, like 1 to the 16 for larger cases. IP-opt requires an indefinite, sparse, direct, inertia revealing solver, and that is actually hard to find one on a GPU. IP-opt only supports direct solvers because direct solvers are usually better if you have very bad conditioning. The exception is Paradiso, so you can switch on the iterative solver, and actually for large cases, it indeed does not converge. The default solver is MUMS. We use the HSL library with their solvers MI27 and MI57, and these tend to be best if you have, as I said, hard problems. There are two parallel solvers, PIPS and NLP, and HIOP, so they are distributed parallel. That's how we wanted to scale up. So PIPS and NLP was what I presented last year, use the Schur complement to parallelize in a distributed way. And now we have it was developed at Argonne by Cosmin Pitra, and now we have we are developing in our project the HIOP solver, which is a mixed dense sparse solver. And as you can imagine, this mixed dense part is crucial because that means that the dense part can be solved on the GPU, and the sparse part will be solved on the CPU. So you can offload something to the GPU. Now, this is what I also presented last year. So this is the first stage is the power grid under normal operation, the optimal power flow, and then you have to protect against all the contingencies, which are scenarios. So this problem is solved in a distributed way as a two-stage optimization problem. We use JUMP, so we had JUMP as a modeling framework. We modeled our grid in JUMP, and then the derivatives and everything was being passed to our solver PIPS. And unfortunately, that way is now blocked since JUMP has no direct support out of the box for GPUs, and also Julia lacks official support at least, or and especially a year ago for Intel and AMD GPUs. So that's why we had to change in our project and distinguish between the critical path and the more high-risk path. Now Julia is only in the high-risk path, and for the critical path, we actually go all C++ and use HIOP as our solver. But we have written a Julia interface for HIOP, so in order to do prototyping in Julia, and you can call HIOP from Julia, but you don't make use of this mixed dense sparse structure, so you don't necessarily make use of the GPU. So what we then want to look into is what if we would start from scratch and would develop an optimization solver specifically for GPUs in Julia? What can we leverage from Julia and from the GPUs? To make that, we simplified our problem first, but wanted to keep the same core components. So we made out of our optimal power flow a power flow problem. This actually kicks out the cost function and the line limits. So the power flow problem actually just gives you the state of your system. So it shows you a solution of your system given that the Kirchhoff's laws are fulfilled. So this then is the system of nonlinear equations, but we still have to use the same core components. We still have a Newton algorithm, we still have to provide the Jacobian, and we still have to have a linear solver that runs on the GPU. As a reference implementation, we use MatPower in MATLAB. So our goal is to compute the Jacobian using automatic differentiation and see how we can extrapolate that to the optimization later. See what we do about the linear solver. So we probably want to go towards an iterative solver, since that is what you should use on the GPU. It scales better. So we implement the preconditioner and a Krylov method on the GPU. The main loop of the computation of the Newton iteration should all run on the GPU. No data transfer should take place from host to the device. All should be written in Julia, no external calls if possible. So let's go to automatic differentiation. Here's a simple Newton-Raphson. You compute the Jacobian, you solve that in your system, you get the next step, you update your x, and then you iterate until f of x is 0, and then you have solved essentially your linear system, jx equals 0. So what we need automatic differentiation for is to get the Jacobian. Essentially what automatic differentiation does, it transforms your code from computing f of x to computing the Jacobian. There are two modes in automatic differentiation, the adjoint and the tangent. The adjoint is very hot at the moment because it's used in machine learning and in the backpropagation there. So you have essentially two functions that you can implement in automatic differentiation, the Jacobian transpose times a vector, or the tangent, the Jacobian times a direction. The adjoint vector usually used when the number of inputs is very high compared to the number of outputs, and the tangent model used when the number of inputs and outputs are equal, or even the number of inputs is lower than the number of outputs. In our case, they are equal, and so we go for the forward model for our case. Still, the size of the Jacobian grows very fast with the increase in size of the system, so with the increase of the number of buses. So we have to somehow make that faster, and what we do is what's called Jacobian coloring. So this is implemented in sparsif tools. We use the greedy algorithm there, and we compress our Jacobian either by row or by column, depending on whether you are using adjoint or tangent. We use the tangent mode here. So we end up with a Jacobian that has only C columns, where C is the number of colors. So that way, when you compute the full Jacobian, you only have to call your AD function, the tangent function, only number of color times and not number of input times. So the complexity goes down to the number of colors times the original function evaluation of f. And our system is indeed very sparse, so this is very useful. The beauty of Julia is that AD is very transparent. You just make a type change and you essentially have it. But not only that. So we have here our forward first order type. We can create a first order type using the forward diff dual numbers. We can even create a second order type by just sticking in the first order type into the dual numbers again. So we have a second order type if you want to compute Hessians for our optimization problem. And we can just put that type then into a vector or into a CUDA vector, and we have a GPU implementation, which is really great and made possible by this awesome package, CUDA.jl. CUDA.jl also implements a parallelization, so a CUDA kernel generation using the broadcast operator, which we also make heavy use of. This really makes it very easy to write GPU implementations. So using that, we get a natural SIMD parallelization on the GPU. So a vector that has only values now has also elements for each color or each direction that you compute, and we just can evaluate the Jacobian in one go by creating a type that has a T1S type with C directions in the type. So computing the Jacobian is just a matter really of a type change. Let's go to the preconditioner and start first though with an overview of the linear solvers. So the linear solvers, as I said before, in IPOP, there's MA27, MA57, and MUMS. There are also CUDA implementations for indefinite sparse direct solvers from sweet sparse, SPQR, and then the CUDA solvers. The CUDA solvers are very opaque. We don't know what they're actually doing. In fact, if you're depending on your structure of your problem and the size, it may as well just decide to run on the CPU. Then for dense systems, we have the very solid BLAS and cuBLAS. They're doing fine. And then if you have positive definite matrices, you can even use troll mods or sprawl assets. And positive definite solvers on GPUs, at least from my experience, tend to scale better than indefinite solvers. Then we want to go iterative solvers. So we have the two packages, iterative solvers and Krylov.jl. Krylov.jl works on the GPU. So you just stick in again a Q vector, and you can just run your GMRS on the GPU. Unfortunately, it does not have a BiCG step implementation. Iterative solver, unfortunately, you cannot just stick in a Q vector. So for the BiCG step implementation at least. So a preconditioner is built in this way, and you may even why are we using biconditioner for both CPU and GPUs in just 200 lines of code, which is very nice for us, and it's not usual for C or C++ implementations. Now let's go to the results. So you can get our package on our team webpage, Exanauts. We have also other research software there. We also provide Julia builds for Summit.
This talk introduces the Julia Vega and Vega-like ecosystem. So what is Vega and Vega-like? Vega and Vega-like is a set of packages that allow you to create rich plots and figures. And here are some examples of figures that were created with the Vega and Vega-like system. The underlying technology for all of this is a set of JavaScript libraries. So here you can see a schematic of the packages involved on the JavaScript side. The rough story here is that anything Vega-like is relatively high level and concise, but you're restricted in the richness of the types of figures you can create. Any Vega-like plot actually is under the hood compiled into a Vega plot, and Vega gives you much more control and power over the kind of plots that you create, but they're also more verbose at that point. The Julia wrapping of all of these packages started with one package called Vega-like, and at this point it has exploded into a whole family of packages that expose different aspects of the Vega ecosystem. some of them are more stable than others on the Julia side. I'll briefly introduce the various roles that these packages play now. The Vega datasets package just provides a bunch of tabular datasets that you can use for example plots. The core packages in this ecosystem are really VigaLite.jl and Vega.jl. And these packages contain structures that hold one particular plot, the VL spec and VG spec structure. And then there are various ways to create such specifications of plots. And then there are things you can do with these plots. On the left-hand side, on the kind of things you can use to create plots, there are, first of all, options in code to create specifications, and I will briefly run over them later. And then there are other packages that also allow you to create these plots. And some of them are actually interactive UI applications more that allow you to click plots together with a mouse. On the right-hand side, things you can do with VigaLite specs is you can display them and you can save them to disk. The display story, though, is a lot richer than it looks here because the Vega ecosystem is tightly integrated with a whole bunch of downstream clients and packages for displaying plots that I will also cover later on. So the normal way to create a VigaLite specification, and there is a similar way to do that for Vega specifications, is the @VLPlot macro. And here's an example. You can just quickly create a whole range of interesting plots with that command. So this is the main entry point that I think 90% of users should use 90% of the time. You can also use a string macro to copy and paste specifications that are in JSON format. That is sometimes handy if you want to copy an example from a JavaScript web page. Finally, you can load specifications from disk because you can save them as files. So here, for example, I'm loading a tabular data set. I'm typing it into a specification that I've actually loaded from disk from a JSON file. Another really nice option is to use Data Voyager to create VigaLite specs. So here I'm loading a data set, I'm typing it into Voyager. It will open an interactive UI that you can see here, and then you can click with your mouse together what kind of plot you want to have. And when you're done with that, you can actually extract the plot into the Julia environment from that interactive UI experience. How can you display specs? Well, if you the vanilla experience is that it shows specs in a browser, but you can also install and load the package Electron Display, and in that case, you get a much richer experience for displaying plots with a thumbnail view and so on. If you're using any notebook environment, for example, Interact or VS Code or Jupyter Lab, all of those clients actually ship the Vega and VigaLite JavaScript libraries out of the box and provide a really rich integration with the Vega and VigaLite ecosystem. So the plots that you create while running inside these environments will look in particularly good, and any interactivity that you, for example, add to these plots will work flawlessly. Saving specs is very simple. You pipe it into the save function, and we support a whole range of file formats, SVG, PDF, PNG, and then specific formats, VigaLite and Vega here. So that is all very simple and should always just work. Here are some projects that are work in progress currently that I hope to finish over the next, well, I'm not making a promise here. The first one is a package called Quick Vega. And my idea here is that it is a package that will have simple template functions to create specifications. For example, a function like histogram that you just pass a vector and it will plot a nice histogram, or a function called pairplot where you pass a data frame and it will create a rich plot for that. So this would be a non-grammar of graphics API for this ecosystem. Currently the package is empty, but it's actually a great way to get started to contribute into this package because it's, it should be a low investment in terms of getting started with this. A second project I'm working on is called Lyra.jl. It's an interactive UI for creating Vega specs. So it's similar to what we already have with Data Voyager, but it targets Vega instead of VigaLite. So what's the difference between these two UIs? Data Voyager is really meant as an exploration tool for data sets. So you get a data set and you want to understand it, and that's where Data Voyager really shines. Lyra, on the other hand, is a tool that allows you to fine-tune a specific plot. That's the niches that these two projects occupy. I should say at this point that the Julia version of Lyra right now is not really functional, but the JavaScript version is actually feature-rich, and it shouldn't take too much time to bridge the remaining problems here. The final package that I'm working on is called SandDance. I have to admit, I have no idea what that is. It's some JavaScript package that integrates with Vega and VigaLite and creates really fancy 3D interactive graphics like the one that I've shown here. And I managed to wrap it in the Julia package, so you can open it, but that's the level of understanding that I have about this package. So that will require a little bit more work. So in summary, the Vega and VigaLite ecosystem is large at this point. It's really well integrated into many things, into many different front ends, into the table ecosystem, into Queryverse, etc. The core packages of this ecosystem are very stable and production ready. They have been stable and production ready for many years, so you can use them day in and day out. And one of the biggest benefits in my mind of this ecosystem is that the real functionality, namely that's all in the JavaScript libraries, is developed by a very large team of researchers that are incredibly talented. So what typically happens is that every couple of months I just update the underlying JavaScript library and we have new features in this ecosystem, and I actually didn't contribute anything to it. So that's my favorite style of working, and I think it means that we will see many more features coming into this ecosystem into the future. And with that, thank you very much.
You can see that these are the dependency edges to be carrying along. This event is, corresponds to this, and after we waited on this event, we can look at C. And this event is used as a dependency edge here, and so while this transpose con is writing to A, we can read from here safely. If we didn't provide these dependencies and events, we wouldn't have written to. Why could JS on that stream and then execute it one after another. So we need to be a little bit careful when we have a situation in CUDA.jl. We need to wait on it in kernel abstractions, add a fast transpose, which is taken from the developer NVIDIA, operate in blocks of 32, and we're going to avoid tell LLVM that we would like a loop to be unrolled. +1 really index in our group and work with a 32. We are into our tile. We care that all of the arithmetic will end up, and we will compress on the CPU. Let's take a simpler function that I can finalize, denotates the have an at uniform statement. I would have said at each loop to make sure that we are not executing code that would be illegal to execute. So, bigger than the performance of the results together, we can see that code right now they're writing a next generation climate model all in Julia. GPUs are good targets for certain classes of scientific computing, as an example, fluid simulations, climate simulations, machine learning, anything that is a stencil-like operation really shines on a GPU. But we also need a performance portability layer because we have to target multiple different kinds of GPUs. We have to target CPU.
Well, I mean, I noticed a lot of problems with running the CPU and GPU code. I mean, I find that I can't write one kernel, I can't write one function that works on GPU and CPU. By the way, hi Ellipse. But I'm trying to find this presentation because I think I've been through this presentation once. I want to find this like an overall like it says how not to write CPU code. So, but how do I write it? Like, where is that? Is there good TLDR kind of tips like this is what you should do? I'm not sure if it's in there.
GPUs as well, but we want really excellent performance on GPUs because they are what is driving many modern supercomputers, and that is where most of the flops are. But we can't leave the CPUs behind. We want to get at least decent enough performance on CPUs. I originally worked on a project called GPU file loops that had some of the same ideas, but it also has semantics that made implementing multi-threading support very hard. And so we went back to the drawing board and looked at what do we need to change. And so that's how kernel abstractions came about.
All right.
In general,
I do remember going through this, and the thing was that if you write, I think I remember that if you write things in this way, it's going to be fast for the GPU, but it's not going to be optimal performance for the CPU. It might be a little bit slower. I think the best way to do this is to write a CPU version and GPU version, which kind of defeats the purpose, you know? No, it doesn't, but it's hard to justify. Given every time I use CUDA, it's either some issues or things I want to do not support it, so GPU and Julia is a wait and see kind of thing.
Already a rich ecosystem to programming GPUs. You can go to JuliaGPU.org and see.
Be interesting to implement some. So the agenda for this talk, I will start by giving a rough overview of the general structure and the functions that are involved in producing output. And then I will mainly look at some examples. So first, how to extend the system for a user-defined type, and then show an example of how the complete system is being used in the wild. So I want to start by looking at what happens in the Julia REPL. So from object to output. So if we have performed the computation and we have the result saved in the variable x, for example, then the following happens. So first, the REPL calls display of the object, And the display function selects a suitable display, as it's called, from an internal stack. So in the REPL, the top display is just the REPL itself. And this display selects something called a MIME format, which is a representation of the object, which the display itself supports. So for example, the REPL only supports text output. And then the last function in the chain is generally show. And the show function is usually the one that produces the output and writes the output to an IO buffer. So in this case, we would produce output of X for the given MIME. So in the REPL, this would usually be text output. So I just want to mention what MIME means, because you will probably hear it a lot in this talk. And MIME stands for Multi-Purpose Internet Mail Extensions. So as you can see from the name, it was originally used for email. But it's essentially a system to describe the representation of an object. So for example, then in email and at web pages and so on. So just as an example, if we take a look at an HTTP request to Google, then we can see that we have a MIME format here, which is text HTML, which means that, okay, this is a HTML page that we are receiving. And in Julia, there is a type which is called MIME, which you can use to represent different formats. So here I just created two of them. So for example, text plain and image PNG. So generally these MIME types have a main type, which is the first one, and then a subtype, which is the second one. So in text plain, text is the main type and plain is the subtype, and image PNG, then image is the type and PNG is the subtype of this category. All right, so let's take a look at the functions that we saw in the chain before. So display is generally the first function that is being called. So it's the topmost function. And I would say that usually display is a behind the scenes function that you as a user don't really need to interact with. Of course, it's sometimes convenient to call display of your object directly, but you probably don't have to implement anything for it. Instead, this display function is implemented by displays and frontends, such as, for example, the REPL, and editors such as Juno or VS Code and iJulia, for example. So here's an example from the Julia REPL. So the REPL implements, or first it defines a struct, which is a REPL display, and then it implements this display function for this particular display. So this display only supports text output. The next function, as we saw in the chain, is called show. First it defines a struct, which is a REPL display from the Julia, for example. The function is implemented as a user is being the functions that we saw in the chain before. So display is generally the first function that is being called. So it's the topmost function. And I would say that usually display is a behind the scenes function that you as a user don't really need to interact with. Of course, it's sometimes convenient to call display of your object directly, but you probably don't have to implement anything for it. Instead, this display function is implemented by displays and frontends, such as, for example, the REPL, and editors such as Juno or VS Code and iJulia, for example. So here's an example from the Julia REPL. So the REPL implements, or first it defines a struct, which is a REPL display, and then it implements this display function for this particular display. So this display only supports text output. The next function, as we saw in the chain, is called show. And the show function is usually the one that produces and writes output in a specific format. So for example, in this call, show IO, and then we have a MIME, and then an object X. So this would write the image representation of X into the IO buffer. And you can of course implement this show function for many different MIME types. There are a lot of them. So for example, there is text plain for plain text representation, text HTML for HTML output, and image PNG for PNG output, and so on. And it's of course possible to implement many of these if it makes sense for an object. And there are also a couple of other functions that we haven't mentioned yet, which is also related to producing output. So I want to mention them here. And the first one is print. And here I'm just quoting the documentation. Print a canonical undecorated text representation. The representation used by print includes minimal formatting. So yeah, print is very basic and it falls back to show actually. And generally you don't have to implement these for your user types. It's enough to extend show. And then there is also write, which is another function. But this one is not really related to output, even though it's similar. But write instead writes binary representation of objects. So there are different ways of customizing the output, and you can do this by passing something called an IO context to the show function. And the IO context is a dictionary-like object which reps an IO buffer, and then you can query this IO context for output options. So just to mention a couple of things you can check for is compact, or limit and color, and so on. So as an example, if we would implement a show function for a plain text output, then we can check if the output supports color, and then we can produce color output. And if it doesn't, then we just produce no color output instead. So let's look at some examples. So here I want to define show for a user type, and first with just a basic representation, which is called text plain. So let's first define a simple type, which I call Julia logo. And if we just create this an instance of this object, we can see that we have some kind of output. So every type in Julia has a default method that will be called, and in the case of a struct, it's just the name and then all of the fields. But in this case, we don't have any fields in our struct. So let's define pretty printing for this type. So we define base.show with this text plain MIME. And then we just print these 3 dots taken from the Julia banner. So now if you look at the object X again, then we see these 3 dots instead of the default output. All right, so let's make an image of this as well. So we can support many different image formats. So for example, PNG or SVG images. And here I have an example from a notebook. So we define the same struct again, and we see the default output in text. And then we define a very simple show method. So I have a PNG file stored, which is called JuliaDots.png. So my show method here just opens this file, reads all of the bytes, and writes them to the I/O. And now we can see that the output has changed from the default text one to this PNG image. And we can do the same with SVG output. So I also have an SVG version of this image. So I just open this file and write all of the bytes to the I/O. And now we can see that we instead see the SVG output. So in this last notebook cell here, there are 3 different methods defined. So we have one with default one with text output in cell number 2, and then we have our defined PNG output in cell 4, and the SVG output in cell number 6. So somehow iJulia chooses to use one of them. So in the last case we only see the SVG, for example, even though PNG and text output is also possible. So I want to take another look at how this works in iJulia. So iJulia is an example of a frontend that uses lots of Julia's display functionality. So first it defines its own display, just like the REPL, and this one is called inline display. And this display implementation supports multiple MIME representations, in contrast to the REPL one, which is text only. So you might have noticed that in a notebook you might sometimes see text output, sometimes image output, HTML output, and maybe LaTeX output, and so on. So the iJulia display is a little bit more rich in that sense. And iJulia actually captures multiple representations of the same object, and then it's up to the front end to decide which of these representations that is being displayed or shown to the user. So if you show a notebook in the browser, for example, you might see image output, but if you show a notebook in like a terminal or in a REPL, then you might instead see the text output. So if we take a look inside a notebook, so a notebook is just a JSON file. So if we take a look at the same notebook as we had on the slides before, yeah, this one. So if we take a look at cell number 2, so in this one we have the input is just the Julia logo, and then we have the default text output, which looks the same. So inside this notebook file, it's represented like this. So it's a dictionary, and we have a source, which is the input to this cell, and then we have output in plural. But when we were at cell number 2, there was only one show implementation, so it's just the text output. But you can see, okay, this is the text output, and it's just the Julia logo, like this. And if we take a look at cell number 4 instead, which was the cell where we had defined also a PNG version of the show function, then we can see that there are actually two outputs stored here. So we have the image, which is base 64 encoded, and we also have the same text plain output as before. But as you saw here on this slide, that the output that we are actually presented with is the PNG version of the output. So it was now the browser or the backend that decided that since we are viewing the notebook in the browser, then we display the image version, because my browser is able to display images. So that's what I wanted to talk about today, and thank you for listening.
Implementing multi-threading support very hard, and so we went back to the drawing board and looked at what do we need to change.
Hello, my name is Stefan Lenz and I would like to present our package Julia connector to you. It is actually an R package, not a Julia package. This brings us to the first question. Why would you be interested in that if you are here at a Julia conference? Integrating Julia in R is also interesting for Julia users because it allows them to share their code easily with R users. Making the gap between Julia and R smaller also helps to establish Julia as an alternative to writing C code. R users can also benefit, of course. If an R developer wants to write some algorithm that will be too slow in R, but does not want to switch to Julia entirely, he or she can optimize only portions of the code using Julia. An R user that collaborates with Julia users can simply access their code or any other Julia code. In the following, I will use Flux as the main example for demonstrating some of the features of the Julia connector. Here you can see how easy it becomes to use functionality from Julia packages in R. For example, if you would like to create a neural network using Flux, you can do this in Julia in the following way. You call dense to create densely connected neural network layers with the given numbers of units and an activation function. These layers can then be connected with the chain function. If you would like to do the same in R, you can use the Julia connector. The Julia connector does not know about Flux, but the Julia import function simply scans a specified Julia package. Everything that can act as a function in this package is translated to an R function and collected in an R environment. With this, you can call the dense and chain function now in R, and also pass the ReLU activation function as an argument. Chaining function calls is possible because object references can be transferred between R and Julia. In the same way, the return value of a function call, here our neural network, can be assigned to an R variable. As you can see, this allows a quite tight integration on the syntax level. It is also possible to couple Julia and R more loosely. The Julia eval function can evaluate arbitrary Julia code that is passed as a string and return the result to R. With this, we can, for example, define a training function for the model by evaluating its definition in Julia. The result of this evaluation is a function that can be assigned and used as an R function. R functions can also be passed as arguments to Julia functions. This allows to call back to R from Julia. Here we see how we can specify a callback function that is executed during the training. For this, we define again a training function that accepts as fourth argument another function. This callback function can be used to communicate the current training loss back to R during the training. This can be used to create a monitoring plot showing the training progress live. A complete example for this can be found in the README of the package on GitHub. When developing a complex deep learning model, we will usually have some function to initialize the model, a training function, and a way of evaluating or using the model, for example, predicting some labels. It makes sense and is also more efficient to collect Julia code like this in a module. Using modules is also a nice way to keep your Julia workspace clean when working interactively, because all definitions in a module are reset every time the module is imported. Loading a module is done with the include function in Julia. We can call this function in R via the Julia call function, which allows to call any Julia function by name. With that, we can load the module definition from the source file. The automatic import of the functions from the module works then as well as with the packages, and we can use all functions in our module in R. Another example where Julia is useful because of its speed is the analysis of large datasets. To demonstrate the handling of tabular data, we use the package JuliaDB. In R, data of tabular structure is kept in data frames. In Julia we have the tables package, which provides a common interface that is implemented by many other packages dealing with tabular data. This interface is also used by JuliaDB. The JuliaDB table function accepts any Julia structure that implements the tables interface to create a special index table. The Julia connector implements the tables interface for an R data frame such that it can be passed to the JuliaDB table function. You can also see here that the Julia connector handles missing values and will translate NA values in R to values of type missing in Julia. With a call to AsDataFrame, you can get a normal RDataFrame object from any Julia object that implements the tables interface, like the object we have created in the slide before. You have now seen the features that are highlighted here in blue in this table. This feature matrix shows the most important features of the Julia connector and compares them with two other R packages that aim at integrating Julia in R, namely JuliaCall and XR-Julia. For the communication between Julia and R, we chose to use a custom TCP protocol. A connection via TCP can be maintained more easily across different versions of R and Julia than using a connection via the C interface as JuliaCall does. XR-Julia also uses TCP, but uses JSON as interchange format, which is much less efficient because JSON is text-based. Communicating numbers via a text-based format requires the conversions to strings with their decimal representation. Our custom communication protocol uses the binary form of the objects and is optimized to create as little overhead as possible. Another advantage of using TCP is that it allows to implement features for interactive use which are not available in JuliaCall. Interrupting long-running calls is possible via the Julia connector in a clean way with this. This is especially important for deep learning. If you experiment with some deep learning model, for example, you may change your mind if a call takes too long and would like to interrupt it. Showing standard output and standard error output, including warnings, is also an important feature for the interactive use. Due to the lack of time, I can't go into the details of the other features here. You can find more details on the features of the Julia connector and on the comparison to JuliaCall and XR-Julia in our article, which is available on arXiv now. It also includes an example for fitting neural ordinary differential equations on time series data. If you have become interested You might want to check out the package on GitHub, take a look at the article on archive, and of course install the package, which is available from the official CRAN repository. Thank you for the attention.
Hello everyone.
Hi, I'm Aaron Christensen. I work at the Goethe University Library in Frankfurt, Germany. I'm talking today about a feature I wrote for Julia 1.5 called the ccall macro. This macro is different from the ccall function in Julia in that it allows a more intuitive Julia syntax. It allows the use of var args of different types. It checks that function pointers are instances of pointer to C void. And it takes away one feature of ccall, which is that it does not support choosing an LLVM calling convention. It just uses the default calling convention. So to unpack those a little bit, if you have a C function like this, size t, string length, and then the argument is a pointer to char or a C string. In ccall, with the old ccall, you would write like this, ccall, and then you'd use. Hi, I'm Aaron Christensen. Welcome to my talk for JuliaCon 2020 about dispatching design patterns. I live in Germany, in Frankfurt. I am a programmer at the Goethe University. So my talk today is about design patterns. The talk has a GitHub repo at my GitHub account, ninja_aaron/dispatching design patterns, where there's transcripts and code samples and links and stuff like that. So if you want to check out anything in this talk in more detail, there is more there. All right, so a design pattern is a formal way of documenting a general reusable solution to a design problem in a particular field or field of expertise, especially in this case, software design. Dispatch, this is not the first definition of dispatch or the second definition, went down to the 7th and 8th definitions. To destroy quickly and efficiently. To pass on for further processing is the next definition, especially via dispatch table. So Julia, in some ways, destroys a lot of traditional design patterns because it is different than what a lot of programmers are used to. Julia looks like Python or Ruby, looks like MATLAB, some other languages, but the objects are actually very different. Julia doesn't have classes. Julia interfaces instead are designed in terms of structs, just simple composite data type. Multiple dispatch, you also have some abstract types in there and stuff. And it's more similar to the object orientation in Common Lisp, which is, I guess, a language far fewer programmers are familiar with. For object-oriented programmers, Julia's objects may be disorienting. So that's what I mean by in the first sense I had of dispatching design patterns. It kind of wrecks what you expected. Now, I answer a lot of questions on Quora about Julia. One of the things people are asking about frequently is, how can you have a large, complex project in Julia if you can't even have classes, right? How can you make appropriate abstractions that scale up? So in some cases, some of the popular design patterns aren't really necessary in Julia, like some of them in Gang of Four, if you're familiar with those. For example, the strategy pattern can just be replaced by passing a function to another function, right? You can do this in any functional language and in most dynamically typed languages. Instead of having a whole bunch of classes to think about your strategies, you can just have a function that you pass in. You go to a party, you come up with your small talk strategy. Maybe you talk about the weather, you talk about your job, have some recent topic. So you find a human to talk to at the party. You use your small talk strategy. Hopefully there's no error, but if there is, you weep deeply and return home. If you want more examples of how some of the classic design patterns are kind of superseded in dynamic languages, Peter Norvig has a talk from 1996 called Design Patterns in Dynamic Languages, which goes over sort of stuff like this, how these design patterns are really replaced by language features in higher level languages. And he also has some more design patterns that emerge in dynamically typed languages. So let's get to encapsulation in Julia. So in Julia, you have structs. A struct is just a name for the type and data fields. Now the data fields each have a name and they have a type. You don't technically have to have a type in Julia, but types on structs is probably the most important thing you can do for the most important simple thing you can do for optimization in Julia. If you don't have the types there, you're going to have really bad performance. On the other hand, you don't really need types on functions as much in Julia, but it's very important to have them for structs. You also get a default constructor, right? So you put in a value for each parameter and it constructs your struct. Attribute access looks like other languages. You got your period. Oh, by the way, all attributes or fields or whatever in Julia are public, right? So any function, any user, anyone can access this data. I wish there was a little bit more way to control privacy of data in Julia, but there is not. So structs in Julia are immutable by default. This is usually good. So we try to change one of the fields in our point, and it doesn't work, right? A point is a point. It shouldn't change. If you have another point, then it's another point. It's also good for performance, immutability. The compiler can see that and do some interesting optimizations. However, some objects do need to change over time. For example, if you have a starship, here we have the Enterprise, right? Our starship has a name and a location, which is the point that we defined previously. And we could change the location of the ship by giving it a new point, right? You can also have alternate constructors for structs. Simply take the constructor name and define another dispatch. This constructor helps us avoid having to write the point constructor every time we define a new ship. You can also have an internal constructor with new. So after your fields, you put in the constructor name again, and then you have how you wanted to use the default constructor, but you use new here because this name isn't available yet because it hasn't been defined yet, right? It's like the chicken and egg thing. So you have this new thing. And once you have an internal constructor, the default constructor goes away. It's no longer available. This can be good for doing sanity checks on variable values or something like this as well. Next, we have methods in Julia. So abstraction in general is about simplifying internal complexity.
or single instruction multiple data, which is a single instruction can operate on multiple elements of a vector at a time. So, modern CPUs, most of them have vector registers with 128, 256, or 512 bits being particularly common. What this means is that a 512-bit vector, for example, can hold 8 float 64 or 16 float 32. So a single instruction operating on these vectors will, for example, an add instruction will then be adding 8 float 64s or 16 float 32s. So you're doing a tremendous amount of work per instruction. And for the most part, there's very little overhead in terms of number of clock cycles that it takes to actually complete, and how many, so like throughput in terms of instruction per clock cycle, it tends to be negligible or no overhead for these SIMD instructions, with exceptions existing for more complex instructions like square roots or divisions. Now, something that is important to hold in mind when you are writing your own code is sort of the layout of your data in memory and how you access it. So I will go over this in a very heuristic manner, and to say that sort of if you wanted to create a vector, sort of represented here in this bracket, of x5 through x8, loading from, this is a vector in a CPU register, loaded from a vector in memory of x1 through x20 or so, that loading contiguous elements like 5 through 8 is very fast. And similarly, if you had this vector register and wanted to store it into your memory, into memory, and you wanted to store it contiguously, that is again very fast. Similarly, even if it wasn't a multiple of 4, or a multiple of 2, one of these power of 2 sizes, that is you could mask off parts of the vector using masked instructions or applying an off-mask register depending on the instruction set, and again, this is very fast. Similarly, broadcasting a single number across a register is also fast, but for example, if you reducing a vector into a scalar, however, is not, and takes multiple instructions to accomplish. Much slower, however, is if you did not have contiguous blocks of memory that you were loading or storing from with your registers. If gathers and scatters, gather being if you had different places in memory that you wanted to load into a single register, and a scatter where you had a register that you wanted to scatter across. These are much slower, and therefore ideally you can arrange your memory layout, to choose a memory layout for your program such that the operations you want to be performing in parallel involve contiguous loads and reads. Now, the other major component of intercore parallelism is superscalar parallelism, which is that multiple instructions can be executed at a time, and that many can be in flight at a time. So on one hand, we had the SIMD, which is that each instruction is working on multiple elements of data. We also have parallelism from there being multiple instructions. The key takeaway here is that because sometimes there are dependency chains, such as if you're trying to calculate A plus B plus C, you would need to wait for A plus B to have finished computing before you can start calculating that sum plus C. Therefore, if your computation was just one long dependency chain, you would have to wait for each instruction to complete before being able to complete the next instruction. And because it's often the case, like for an add instruction, that recent CPUs are capable of executing sort of two with a throughput of 2 per clock cycle, but it takes 4 cycles for any particular one to complete. That basically, you, instead of achieving the 2 per cycle, if you had a dependency chain, you would be limited to 1 every 4 cycles. So as an optimization, you have to sometimes unroll a loop to, rather than accumulating into a singular number, you have multiple accumulations. That way you are still able to, this is so that way you're able to take advantage of this superscalar parallelism. So we're making sort of an example that hopefully you can sort of visualize, or by just seeing this code and seeing how we change it to take account of first a SIMD optimization, where we replace this scalar sum when we have a dependency chain, where we're adding to this one number every time in the loop, to now adding 4 numbers at a time within this loop. We sort of unroll this loop for this vector width of 4, and then we're adding 4 at a time as for the SIMD optimization. Then the next optimization here for superscalar parallelism is that we'd said hypothetically that we have potentially 2 additions per clock cycle, and it takes 4 clock cycles to complete. So on each iteration of this for loop now, we have clock cycle 1 starts adding these 2. Clock cycle 2 begins adding 3 and 4. Then 5 and 6. Clock cycle 4 adds 7 and 8. And then clock cycle 5, these 2 additions are done, and we can begin the next 2. So now with this, we're able to achieve the 2 additions per clock cycle. And each addition is also adding 4 numbers. So that ideally this would be a rather fast summation algorithm, or summation implementation. Of course, not actually written like this, like you wouldn't be slicing arrays like this, but just sort of representing the actual operations that are being performed here. And then at the end, we have to sum up all our accumulation vectors into one vector, and now finally we can turn this vector into a scalar. So this is also something that for the most part LLVM does, and Julia does by default very well. Something that is missing from this example, of course, is that tragically, by some cosmic oversight, not all vectors happen to have lengths that are a multiple of 32 or 64. I don't know why not, but it just seems to be that that's the case. So we have to handle the remainder. And now what LLVM does for the remainder is it adds one of these scalar loops to just finish off the remaining 0 to 31 elements. However, unfortunately, it's the case that this is actually much slower than, many times slower, because then we don't have any of this parallelism at all, than this vectorized portion. So even if a vector is very long, it is easy for the remainder to take longer to sum up than than it is the vectorized portion. And we can see that here with, by running benchmarks, where I adapted the sum example to being a squared norm. So instead of sums, we have FMAs. And now here I'm benchmarking this vector of length 799, 768, and 800. And we can see that it takes roughly twice as long to do 799 elements, over twice as long as it does to do 768 or 800. So this remaining 31 on top of 768 takes longer than it does to do the 768, which is, of course, less than ideal. Now this, as a note, this problem is exacerbated in AVX 512, like this computer that I'm running on has, because now we have, we have a longer remainder longer unvectorized remainder. So with AVX2, it will be on average half the remainder. Therefore, the problem is half as bad. But this is still not an ideal scenario. Now, one of the optimizations that loop vectorization does is that it also vectorizes the remainder of the loop. So that way, when we do 799 elements, instead of being over twice as slow as 800, it's more or less, it's barely slower at all, and roughly in line with the performance of 768 or 800 elements. So now, when you have loops that are likely to be dominated by this remainder calculation, which is going to be more severe the shorter your loops are, then that would be likely a place where using loop vectorization and add AVX is going to be profitable. Another case where it's profitable is special functions like log, because the base Julia log implementations are not, or log, sine, cosine, EXP are not vectorized, while loop vectorization uses a different implementation that is SIMD, and therefore it's able to calculate this log determinant of a triangular matrix much more quickly than, for example, the implementation in the standard library linear algebra. I mean, we can look at another example here that I don't want to go into too much detail, just showing like workarounds of some of the limitations, and also note sort of a memory layout of struct arrays as a library that maybe you should look into at your own time, but is something that can sort of work around the fact that imaginary and real numbers tend to be interleaved, which, as we said, is sort of not what we want because we're doing SIMD across loop iterations. So structive arrays now suddenly makes all of the imaginary and all the real numbers contiguous, and then loop vectorization gives us a SIMD syncos, so that now we can calculate cosine imaginary sine much more quickly than the base implementation. So now, another area or another optimization that loop vectorization provides where we can get a substantial performance benefit is in that it tries to eliminate any redundant loads that it can. Well, any redundant operations, but the most extreme examples, the redundant operations are loads. So what I mean here is that if we look at this sort of matrix multiplication example, we have here an inner loop where this FMA operation of A times B plus C depends on all three loops, but loading from A does not depend on N, and loading from B does not depend on N. And similarly, I mean, we don't need to sort of store, well, I guess we already wrote that we are only storing C when we're done. But, so, you think of the sort of the basic idea here is that we want to sort of reload these as infrequently as possible. So by unrolling both the M and the N loops, we get to reuse A for every time we unrolled N, and we get to reuse this B load for every time we unroll N. So by unrolling both of these loops, we have a lot of reuses of this data, and if we call, let's say, U1 and U2 the times that we unrolled the M and N loops, then we have sort of U1 plus U2 total loads versus U1 times U2 FMAs that we're capable of doing. So that sort of really mitigates this sort of memory problems and load-bound nature of sort of how this loop was actually written, and lets us actually begin to saturate the two potential FMAs that we're capable of doing and achieve a lot of gigaflops that way. Now, this is here I just made a very small size problem just to show how, I guess, easily we can gain much better performance over the static arrays implementation by just defining a couple overloads. Here, check args is to allow M arrays to actually use loop vectorization. By default, arrays that are not dense would opt out. And then we also want to be able to, loop vectorization to be able to learn the actual dimensions of an M array. So we can define these to do so. And for good measure, I also create regular base Julia arrays that I evaluate this on to show that even the base arrays are, for 7x7 arrays, that this is much faster than the static arrays or the M arrays. And loop vectorization, given static size information, is, again, over twice as fast as it was without. So, I mean, it's very easy to make sort of these optimized small matrix operations in this manner. A little more interesting for most people is probably that the flexibility of, if we come up with like sort of arbitrary tensor multiplication like things, that we're also able to apply it there. So here I show einsum, which just creates a bunch of loops and adds SIMD. Teleo, which uses loop vectorization, if you loaded loop vectorization as a just convenient means, because I think most of us really like this index notation. And then finally, in case you want to see what the actual loops.
Hi all, my name is Bart Janssens. I work at the Royal Military Academy from Belgium. Welcome to my CXXwrap.jl talk for JuliaCon 2020. CXXwrap is a package to allow you to use C++ libraries from within Julia, and it consists of a C++ part and a Julia part. The basic approach in CXXwrap.jl is that we use a library-based approach. So we compile a C++ library, which of course has to be written completely in C++ using all the standard C++ tools. And then we can, for example, distribute this using Binary Builder and Yggdrasil, and then use it from within a Julia package. This approach is actually inspired by Boost Python and PyBind 11. So if you have a C++ library that already has Python bindings using these systems, it should be very easy to transition to CXXwrap. It is non-interactive, so if you want more interactive use of C++, or if you want to inline C++ into Julia code, then CXX.jl would be the way to go for that. We also provide some tools for more easily accessing Julia from within C++, so providing some C++ style interfaces to things like Julia arrays. And finally, there are some wrappers for the standard library containers, also mapping them to standard Julia interfaces. For example, a standard vector implements the array interface. So we'll start off with a small demo of how the CXXwrap package works. So let's say we have a class named foo with a constructor that takes an integer, which sets the private data value m value to the value that's passed to the constructor, and with one single member method add that adds an integer to the owned value and then returns the sum of the two. So to wrap this class into Julia, we have to first include the CXXwrap headers in C++, which will provide us with a macro and a C++ class that represents a Julia module. We then can add types and functions to this module, so using add type to add the class that we defined, and we can add a constructor and add the method that has to be exposed to Julia. So that's the C++ part. Then from within Julia, we use this from within our own module. I create a module here called libfoo, where we first call the wrap module macro on the compiled library file, which is named libfoo here. If you don't supply the extension, it will automatically pick the correct one for the platform that you're on. And what this does is basically build a static table of all the methods that exist, which will then be filled at runtime using the init cxx macro. So this distinction between wrap module and init cxx is needed to make it possible to support pre-compilation. And then finally, once these two steps are taken, all of the types that are defined on the C++ side will be available on the Julia side. So we can now export, for example, the type foo and the add.
Hi everyone, welcome to my lightning talk about continuables, a little package of mine, Python yield in Julia and blazingly fast. I'm Stefan Sam, working as a data science consultant in Munich at a machine learning reply company. I really like to do applied machine learning, especially probabilistic stuff, also abstract programming like functional programming and category theory. Continuables implement yield-like generators like found in Python using plain functions. As the Julia compiler is very good at optimizing through functions, it can produce maximal optimal code. Let's take a look. So I came from Python. I wanted to have this nice yield syntax. You see it on the right, where you just can use whatever code you want and build a generator out of it. That's possible in Julia with channels. However, they are quite slow. So coming to Julia, of course, I wanted to have it fast. The second motivation is that I always like to have my packages, my tools right. And yeah, so the Julia comes with some standards and base iterators and also iter tools and also base itself. But the iterators are just not flexible enough, that's just said. So that was my goal. I wanted to re-implement these key helpers on top of a little bit more flexible type, which is at least faster than channels. And it worked out. Let's take a look. So that's the basic implementation. You see, it's just a simple wrapper type containing a function. And the little syntax support is that if you call it, it just forwards the single argument to the function. This is, I call, a continuation. So the next one is already the definition. So we wrap it into our continuation and then have an anonymous function which gets this continuation. And you see, we use the continuation now just as we would have used the yield. And that's the key idea. So we replace the yield syntax with just a function which we later get, which then continues. So here we go for all numbers from 1 to 10 and continue. We can then call this continuable, this generator, with the function as you would do. And we have both syntax available, just the anonymous function and also the do syntax, which is quite nice here. So this has a couple of advantages. And the main one is that the compiler can actually kick in and optimize anything because Julia compiler really knows well about functions. And also the definition is quite intuitive as well as the meaning. So we just have a continuation function which we get. There are some disadvantages though, and the big one is that we cannot use for loops, but we need to use this do syntax instead. It's kind of the alternative for loop for here. The reason is that the for loop uses the iterator protocol, where you actually need to full stop the execution at a point, and later on you need to be able to recreate where you left off. And that's just not possible with functions in this general setting. So we cannot implement it, at least not without losing performance. So we implemented it, but falling back to channels. And similar, it's also not possible to implement the zip. So where you get two iterators and you want to combine them into one, which goes over kind of all tuples of the one and the other. So that's also not possible because you need a full stop, which we cannot just full stop a function in between. And another little thing I'm going into in the performance section is that you have to be careful about local variable reassignment, but we'll see it soon. So the package supports one extra macro, which makes it super handy to define these continuables, and that's the cont macro. So here you can see we just write this macro around and we'll wrap our stuff with an anonymous function and with the continuable type. We can just use it, and here you see a nice syntax. You can use also the for each instead of the just extra call. And yeah, so you can write it like that. Quite neat because you can read it aloud and it just sounds good. For each and the continue will do something. Now let's take a look. So how does this look like with the little example from the beginning? You see we can directly map it. So that's the neat thing I wanted to have. We have just this yield syntax, the feeling, and we can just get it over. And also getting another continuable, another generator in it just works with this for each loop. So where we can just go through the other continuable. Going to the performance, here on the left side, I've written two functions to sum up the values in one of these continuable containers. And the first one is kind of the optimal one, and the second one not so. And you see that the key is that you define another reference, which you then update instead of updating the variable directly. You see the difference in speed is really drastically. That's a factor of 20,000. The first is nanosecond, the second is microsecond. And because this is so crucial, the package comes with a macro which helps you along with this, so that you don't have to write these brackets all the way, but you can just use the macro as put on the right. So now take a look at the comparison performance with others. So leftmost is the plain iterable, and you see it just has the very same performance as our continuable. Of course, that's a simple case, but still good to know that the compiler can kick in and optimize everything away. So that's really nice to have. In the middle, you have the channel implementation, which is an amazing 20 million slower. So that's milliseconds instead of nanoseconds. And yeah, the function just converts an iterator to the respective channel. And on the right, you see another package which also try to do the same, but a different attempt. So here you can also use the for loop syntax, but as you see, it's in the middle in performance. So it's hundreds of microseconds. So still much slower for this simple case. Okay, so it worked out. I was able to create kind of this syntax, which suits for many use cases. And you can do it with a simple macro cont. You have to, however, keep in mind some things. So use the do notation instead of the for loop. This is just way more performant. And if you want to update local variables, use the refs and just a nice macro. And be aware that if you need to use zip, you can do that, but it falls back to using channels and it's just not that performant. And as said in the beginning, there are many helper functions in this package, continuables, and yeah, so this is a list of them. Try it out. Thanks for joining today in my lightning talk. Take a look at my GitHub continuables, and always feel free to contact me. My nickname is schlicht anders. Thanks for joining today.
Good day to you across time and space. My name is Gregor Kattmer, and my experience with parsing grew in 25 years of scientific computing and coding. Today, I'm focused on text research and psychometric theory. This lightning talk, Iterable Parser Combinators for Fast Parsing in Pure Julia, demonstrates the Julia package combined parsers. Parsing is everywhere, literally. Countless parsing libraries exist, so why another one? I had discovered Julia and got enthusiastic about types. When I migrated my parsers, I removed the tedious part of interfacing parser language to take apart with programming language to recombine. The title slide defines taking apart and recombining both in one expression. Robust parsing with type checking that cuts development time. In the following 7 minutes, I will demonstrate combined parsers, which is interoperable with regular expression, text parse, and with an API to include custom parsers, and integrates into the general Julia-based API for parsing, matching, and iteration. It's fast like the PCRE-C library, thanks to the amazing Julia compiler. And the second part of the talk then is a showcase for the brief syntax of combined parsers, which enables reasoning about the parser instead of obstructing, like regular expressions tend to do. If you disagree, check out the palindromes example in the manual. So regular expressions are the standard to parse. The ER string macro constructs a combined parser from a regex. The regex syntax and structure are laid out side by side with the combined parsers API. This regex example repeats A any number of times, B at least once, C optionally, and so on. So you can simply replace R quotes to RE quotes in your code and use the base match API. Note, when you regex capture D matches repeatedly, you get only the last match. With combined parsers, you can transform with nesting and capturing such repeated values into actually any Julia type. Julia's iterate API lazily parses with backtracking combinatorics if a parsing is not unique. Similarly, all matches in a string can be iterated. The RE-string macro features PCRE compliance. Tested with the PCRE-C library unit tests, the package is succeeding in over 3,000 tests on nearly 1,000 regular expressions. Failing cases are discussed in the manual. Features include basics, atomic and capturing groups, back references and subroutines, conditionals, and lookarounds. The same unit tests are used for benchmark comparisons with PCRE. Most benchmarks are faster with combined parsers, as indicated green in the scatterplot of timings on log scale. On average, combined parser is 26% slower than regex, however, because regex captures perform badly compared to the recommended approach in the showcase that follows now. This simplified showcase in a few lines defines a combined parser from scratch, much like the packaged RE string macro does in about 600 lines. A simple regex consists of some repeatable pattern, here simplified any character, and a repetition suffix or no quantifier when the character is matched exactly once. Note that the result types are inferred. Repeated patterns are repeatable patterns followed by repetitions transformed into a combined parser's repeat. Simple regex then chains any number of such repeated patterns and transforms them into a combined parser's sequence. This is sufficient for cases without curly braces. Custom repetitions are in curly braces, with a minimum number of repetitions as a text parse numeric, followed optionally by a maximum number of repetitions, a comma, and maybe a second numeric. If the comma is missing, max is missing the value. If the max number is missing, it defaults to 1,000. The result time is a name tuple with min and max values. The name tuple is then mapped to a unit range, handling missing max values. If you forget this transformation, a type error will be thrown because it does not match the repetitions result type. This saves time. The simple regex showcase is a functional combined parser resulting in a parser. The ABCDE repetition successfully parses the sequence way back in the first example. I'm thankful for many great works, most notably Julia's parametric types and multiple dispatch compiler. Scala's fastparse package, the Elm parser, because functional parsing is great. Parser Combinator was an inspiration. It does, however, not follow Julia 1.0 iteration API and small unions. Combined parsers is focused on regex, text parse, and most importantly, types and compiler optimizations, and thus no fork of Parser Combinator. Automat.jl provides deterministic finite automata with actions. Actions make code rather convoluted with enter, exit, mark, and emit. It would be interesting to investigate interoperation when Automa supports varying code lengths and UTF-8. This brief talk could not list all features of combined parsers. Fast prefix tree parsers are included in the package, and parsers can even arbitrarily depend on the parsing itself, for example, to balance tags in XML. Memoization, side effects, and logging are supported, and more. The documentation provides user manual and tutorial. There is a comprehensive package for Wikitext. More is coming. Next is primarily the syntax trees based on your feedback and optimized transformations. Julia type inference in combined parsers helps automate the data pipeline. maybe combined parsers can help with some of your work. I will be glad to support if you have any questions. I'm maintaining combined parsers actively. Based on this work, I now focus to release the filing forest platform, which is ensuring schemas for tables and GraphQL from your parser-defined data domain, even for recursively nested types, and enabling efficient computations. These currently proprietary packages are default over configuration for fast integration. Please contact me for collaboration. Thank you.
Alright, thank you. I think that's done enough watching JuliaCon. I love the video I've watched already. Pluto still my favorite. Yeah, alright. Hope to stream some other time. Alright, thanks Ellipse for tuning in. Thanks Open Sources. Thanks 3Mint. Hope to see you next time. Bye.